In this problem, we're given a collection of 10 variables, x1 through x10, where each xi, is a uniform random variable between 0 and 1. So each I is uniform between 0 and 1. And all 10 variables are independent. And we'd like to develop a bound on the probability of the sum of the 10 variables, 1 to 10, being greater than 7, using different methods. So in part A, we'll be using the Markov's inequality, written here. That is, if we have a random variable, positive random variable x, the probability x is greater than a, where a is again some positive number, is bounded above by the expected value of x divided by a. And let's see how that works out in our situation. In our situation, we will call x as the summation of I equal to 1 to 10 xi. And therefore, e of x is simply 10 times e of x1, the individual ones, and this gives us 5. Here we used the linearity of expectation such that the expectation of the sum of the random variables is simply the sum of the expectations. So now we can invoke Markov's inequality. It says x greater or equal to 7. This is less than e of x over 7, and this gives us 5 over 7. For part B, let's see if we can improve the bound we got in part A using the Chebyshev inequality, which takes into account the variance of random variable x. Again, to refresh you on this, the Chebyshev inequality says the probability that x deviates from its mean e of x by more than a is bounded above by the variance of x divided by a squared. So we have to actually do some work to transform the probability we're interested in, which is x greater or equal to 7, into the form that's convenient to use using the Chebyshev's inequality. To do so, we'll rewrite this probability as the probability of x minus 5 greater or equal to 2, simply by moving 5 from the right to the left. The reason we chose 5 is because 5 is equal to the expected value of x from part A, as we know before. And in fact, this quantity is also equal to the probability that x minus 5 less equal to negative 2. To see why this is true, recall that x is simply the summation of the xi's, the 10 xi's, and each xi is a uniform random variable between 0 and 1. And therefore, each xi, the distribution of which, is symmetric around its mean, 1/2. So we can see that after you add up all the xi's, the resulting distribution x is also symmetric around its mean, 5. And as a result, the probability of x minus 5 greater than 2 is now equal to the probability that x minus 5 less than negative 2. And knowing these two, we can then say they're both equal to half the probability x minus 5 absolute value greater equal to 2, because this term right here is simply the sum of both terms here and here. At this point, we have transformed the probability of x greater or equal to 7 into the form right here, such that we can apply the Chebyshev's inequality basically directly. And we'll write the probability here being less than equal to half times applying the Chebyshev inequality, variance of x divided by 2 squared. Now 2 is the same as a right here. And this gives us 1 over 8 times, now the variance of x we know is 10 times the variance of a uniform random variable between 0 and 1, which is 1 over 12. And that gives us 5 over 48. Now let's compare this with the number we got earlier from using the Markov's inequality, which was 5 over 7. We see that 5 over 48 is much smaller. And this tells us that, at least for this example, using the Chebyshev's inequality combined with the information of the variance of x, we're able to get a stronger upper bound on the probability of the event that we're interested in. Now, in part B, we saw that by using the additional information of variance combined with the Chebyshev inequality, we can improve upon the bound given by Markov's inequality. Now, in part C, we'll use a somewhat more powerful approach in addition to the Chebyshev inequality, so-called the central limit theorem. Let's see if we can even get a better bound. To remind you what the central limit theorem is, let's say we have a summation of I equal to 1 to some number n of independent and identically distributed random variables xi. Now the central limit theorem says the following. We take the sum right here and subtract out its mean, which is e of the same summation. And further, we will divide it out, or we call it normalize, by the standard deviation of the summation. In other words, the square root of the variance of xi, of the sum of xi. So if we perform this procedure right here, then as the number of terms in the sums going to infinity, here as n goes to infinity, we will actually see that this random variable will converge in distribution in some way that will eventually look like a standard normal random variable with mean 0 and 1. And since we know how the distribution of a standard normal looks like, we can go to a table and look up certain properties of the resulting distribution. So that is a plan to do. So right now we have about 10 variables. It's not that many compared to a huge numbering, but again, if we believe it's a good approximation, we can get some information out of it by using the central limit theorem. So we are interested in knowing that probability summation of I equal to 1 to 10, xi greater or equal to 7. We'll rewrite this as 1 minus the probability summation I equal to 1 to 10, xi less equal to 7. Now we're going to apply the scaling to the summation right here. So this is equal to 1 minus the probability summation I equal to 1 to 10 xi minus 5, because we know from previous parts that 5 is the expected value of the sum right here, and divided by square root 10 over 12. Again, earlier we know that 10 over 12 is the variance of the sum of xi's. And we'll do the same on the other side, writing at 7 minus 5 divided by square root 10 divided by 12. Now, if we compute out the quantity right here, we know that this quantity is roughly 2.19. And by the central limit theorem, if we believe 10 is a large enough number, then this will be roughly equal to 1 minus the CDF of a standard normal evaluated at 2.19. And we can look up the number in a table. And this gives us the number roughly 0.014. Now let's do a quick summary of what this problem is about. We're asked to compute the probability of x greater or equal to 7, where x is the sum of 10 uniform random variables between 0 and 1, so call it xi. We know that because each random variable has expectation 1/2, adding 10 of them up gives us expectation of 5. So this is essentially asking what is the chance that x is more than 2 away from its expectation. So if this is a real line and 5 is here, maybe x has some distribution around 5, so the center or the expected value is at 5. We wonder how likely is it for us to see something greater than 7. Now, let's see where do we land on the probability spectrum from 0 to 1. Well, without using any information, we know the probability cannot be greater than 1. So a trivial upper bound for the probability right here will be 1. Well, for the first part, we use Markov's inequality, and that gives us some number which is roughly equal to 0.7. In fact, we got number 5 over 7, and this is from Markov's inequality. Oh, it's better than 1, already telling us it cannot be between 0.7 and 1, but can we do better? Well, the part B, we see that all the way, using the additional information variance, we can get this number down to 5 over 40a, which is roughly 0.1. 1. Already that's much better than 0.7. Can we even do better? And this is Chebyshev. And turns out we can indeed do better. Using the central limit theorem, we can squeeze this number all the way down to 0.014, almost a 10-time improvement from the previous number. This is from central limit theorem. As we can see, by using different bounding techniques, we can progressively improve the bound on the probability of x exceeding 7. And from this problem, we learned that even with 10 variables, the truth is more like this, which says that the distribution of x concentrates very heavily around 5, and hence the probability of x being greater or equal to 7 could be much smaller than one might expect.